Pajamas is down, huh? Okay. Thanks for letting me know. Can everyone hear me at home? Okay, good, good. All right, so let's get started. All right, so first of all, I hope you enjoyed your break. I hope you had your rest and that your batteries are all recharged again and re-energized, rejuvenated. Last lecture we began talking about the structural coverage, one of the biggest chapters of this course. We've talked about a number of concepts. Most importantly, what is a node, what is an edge, what is a graph, and what is a path, the difference between what is a path and what is a test path. Can somebody remind me? I'll be impressed if somebody can remember that. But can somebody remind me what is the difference between a path and a test path? I'll give you a hint. A test path is a subtype of a path. Okay, Nasser, go ahead.
A test path has a beginning and an end that is a starting point of the application and an end point in the application.
Yes, I mean it has to start from an initial node. This is a terminology we like to use, but you're right, and it has to end at a final node. Whereas just a path, okay, just a path within the software doesn't have to begin anywhere or end at anywhere, as long as obviously there's a logical set of edges that connect you between the different nodes. Okay, so if you have to jump, then that doesn't count as a path. We've explained the concept of length, subpaths, and reaches. We've explained the differences and how you want to be able to annotate an edge. Okay, so you put a square bracket to annotate denote an edge. If you want to say more than one node or even multiple edges, you just put them around brackets like 0, dash, 1, and 2. And we said, yeah, that the test path has to start at a initial node, whereas and finish at a final node, whereas a regular path doesn't have to begin at initial node and final path. Okay, there is a special type of graphs called SESC, which means single entry, single exit, and these tend to have just one exact initial node and one exact final node. Okay. I shouldn't probably show the. Can somebody tell me how many paths exist in that little graph that we have over here?
Four.
You can type it in the chat if you want to. Can
Test
somebody
path.
explain how many paths? Sadun, can you tell me how many paths in this graph?
There is a lot of paths, but test paths there are four.
Okay, so no. So 4 is test path. Now it's a trick again. I was just explaining the difference. So path, there's a lot of paths. Okay, even just 1, 2 is a path. Sorry, 1, 3 is a path. 3, 5 is a path. 3 on its own is a path. Okay, but test path is only 4. Okay, now you gotta take into account the diagonal effect as well. Huh? No, there isn't. There isn't. There's just a lot. You just, I mean, I'm sure there's a finite set at the end, but there's a lot more than just 4. I know I would be basically asking you a lot to list down all the different paths for something like that. So you'd be putting down quite a bit. And it'll be a rather silly question, to be honest. Okay. So yeah. All right. We I'm not sure if we explained those. So a visit, again, more terminology. A test path P visits a node if P is in that path. So that's a pretty obvious. And if this thing that we're visiting is a number of nodes connected with each other, in other words, a smaller subpath, then we say we tour it, okay? So visit applies to a particular node when that path is visiting that particular node. If there is a little subpath, a number of nodes that we're visiting from a bigger path, then that is called a subpath, sorry, a tour. All right. So we visit nodes, we visit edges. If you have a node 0, 1, 3, 4, 6, okay. If I want to visit, that visits nodes 3, 4, and 6, and so on. Even the edges are so on. But if we're talking about a little subpath, like say 0, 1, 3, which is part of the path 0, 1, 3, 4, 6, then this is called a tour subpath. All right. So when we say the word path and the small letter t, this is the particular test path that will executed or would be have been toured had we executed test t. And remember, anything with a capital means a much bigger set. So a path of a capital T, T here is a set of little t's. And when we say path brackets T, capital T, that means this is the total set of test paths that are executed had we executed the total set of test cases that we have. Okay. Each test case executes one and only test, not necessarily the same path. We're going to talk about that in a moment. A location in a graph, be it a node or an edge, can be reached from another location if there is a sequence of edges from the first location to the second. In other words, there has to be some sort of a physical connection that connects us to it. Okay, and this physical connection is what we call a syntactic reach. In other words, a subpath exists in that graph that somehow there's the arrows connect. Okay, now there's another thing called a semantic reach, which means that a test case can actually be executed to take me through that path. Sometimes I end up with a situation where I have a path in my graph that I cannot find any test case to take me through it, okay? And I'm gonna give you a little example. Let's just say you have an if statement, okay? You have a little if statement. So it means I'm coming over here and I get to this node over here. I have a little if statement so I can go to either node 2 or I can go to node 3. So from a syntactic reach, as I'm coming down, I can reach node 2 and node 3. There's a logical connection of edges that allows me to reach node 2 and node 3. Now, what if this if statement that is at node 1 is saying something like x has to be bigger than 0 and x has to be smaller than 0? Well, that's just not possible. Okay, x will never be bigger than 0 and smaller than 0 at the same exact time. All right, which means I'm always going to take one of those branches and I might not take the other branch of that if statement. So number 3, node number 3 over here, there is a syntactical reach. Yes, the software doesn't actually know that there is no logical way to reach that path via a test case, but semantically, there is no semantic reach to node number 3 because we're always going to end up taking the other branch anyways. All right. So we're saying something like every test case, it executes a path. Sometimes more than one test case ends up executing the same path. This is very, very common. Okay. So something like, assign grade A, if a student gets 95 to 100, well, 95 will take me through a particular test path. 96 will take me to the same, 97, 98, 99, and 100 will take me to the same test path. Okay. And this is what we call deterministic software, which a test case always executes the same path. And it's obviously valid for one-to-one relationships. Okay. Um, in situations where a test might end up executing more than one test path, this is what we call undeterministic software, where for some reason, whatever the way you've coded it, there's no particular guarantee which branch of the software it will actually execute. Now, in theory, there's no such thing as undeterministic software. And it's usually a big topic of debate of, can a computer really end up creating a random generator? Okay. Well, a random generator is, the computer still can't think of random numbers. It uses a timestamp, a current timestamp, and it just inputs in some sort of a calculation in order to produce that random number. But ultimately, still, it is executing code in a deterministic way. All right. So in those test cases that you see many to many, there's tend to be other input that we don't see. All right, which is related to the state of the system and related to, for example, like say a timestamp. This is how random number generators work. That is also involved in the formula to end up the situation where we have a many-to-many test cases to test path situation. So it's non-deterministic software. All right, now we're getting to the business end of structural coverage. Now we use graphs in testing the following. Okay, we develop a model of the software as a graph, and we're going to be talking about this a little later on in this chapter, because these graphs, these pretty little graphs that we're drawing and that we are going to be doing all these sort of analysis, coverage criterion on, what are they at the end? Okay, they're not just nice little pictures that we are working with. They are abstract representations of the code that we have. Okay, and as I said before, remember the football pitch example, the football field example. Ultimately, what we're going to have is we're going to have a coverage criterion, okay, which is a level of thoroughness that we're going to want to go through a particular graph, which is representing the code. And that level of coverage criterion, the higher it gets, the more work is required. But obviously, the better the confidence that we have in the software that we've developed had we satisfied the coverage criterion. And every coverage criterion, it results in a set of requirements. So basically you say, well, if you want to satisfy coverage criterion level 1, this is the test of requirements. This is the set of test requirements that you need. Okay? A big capital TR with a whole bunch of little TRs. Okay. And then if you go to coverage criterion level 2, then the set of test requirements are going to increase. Okay, and every coverage criterion level subzooms. Okay, you're going to hear this word quite often, subzooms the level before. Okay, meaning that the test requirements that is needed for a higher level coverage criterion usually contains the entire set of test requirements that are required for a lower level coverage criterion. Okay. Now, ultimately, what we do is we don't execute test requirements. We don't create them. We identify them. But what we create is the test cases. So we create the test cases. All right. They execute certain paths in my code, and when I execute the certain paths in my code, then I'm satisfying certain test requirements. All right. If I've satisfied 5 out of 10 test requirements, that means that the set of test cases that I had, the path with a capital T in brackets, have achieved 50% satisfaction. We call it satisfaction. All right. If the test cases have executed different paths in my code, in my graph, which have satisfied, which have satisfied the entire set of test requirements, only then that I can say I've achieved 100% coverage of my criterion. All right. Is this clear for you guys at home, Sadun? Okay. Now, coverage criteria comes in two flavors. The first of which is called structural. Now, when we talk about structural, we don't really care about variables and data and so on. We're just talking about the control flow structure of a code, a source code, which we're representing as a graph. Okay. Now, data flow coverage, it's a little bit more, but in data flow coverage, yes, we're using the same graph, but what we're really caring about is how the data is flowing from one node to another when it got defined until the point it got used. Okay. And that makes perfect sense when I say when it got defined until when it gets used, because if I define a variable and I never use it, it's never really a point of contention. Okay. It's never really a thing to test anyways. It's only when something that I've defined that I've actually used at some point where I'll say that from this point to this point, something could have happened. Now I want to test it. Okay. And obviously you cannot use a variable that you have not actually defined. Okay. This is def use coverage coming up after we've finished structural coverage. But what we're going to be doing for the next, maybe this lecture and the next lecture minimum, is we're going to be focused on the structural coverage criterion. Okay. And we'll begin very, very simple. We'll begin with node coverage. And node coverage means that had I had a graph, I need to have test requirements to say what are the nodes, and then I need to execute, create a set of test paths that get me to reach all the different nodes. Okay, so the test requirement contains each reachable node in the graph. Okay, all right. So if I have a graph that looks something like this, 1, then a 2, okay, then my test requirement set, okay, is 1 and 2. This is my test requirement. Just go to nodes 1 and 2, okay. I could have satisfied both test requirements in one shot by creating a test path that just goes straight through highway 1. So one test case, one stone hitting two birds sort of thing, would have satisfied the two requirements that I have. Okay, remember, this is not at this bottom here. This is, I'm not trying to say this is edge 1, 2, or this is path 1, 2. No, this is test requirement number 1, test requirement number 2. Okay, let me write that down in a different way. So I have test requirement 1 means go to node 1, test requirement number 2, go to node 2. And when I went through the yellow line, I would have satisfied both requirements. And as such, I would have satisfied the criteria. Okay, I know it's very, very simple, but the way I'm writing down what a TR means and so on makes a big difference in understanding what's going to be coming up in the more complicated criterion. Next up, we have edge coverage. Edge coverage a little stronger than node coverage, and in edge coverage, the test criterion says each reachable path of length up to 1 inclusive ng. All right. Now, In the previous graph over here, my test requirement would have said edge 1, 2. Okay, would have said edge 1, 2, which again would have been satisfied with the same test requirement. Now, the reason edge coverage is a little stronger, okay, if I have a situation, for example, like this, let me just think of a good example. I'm just trying to brainstorm a quick example in my mind. Yes, okay. Here's an example, okay? So I got the situation over here. 1 going to 2, and 1 going to 3, 3 going to 2, okay? And this 2 could be an end node, and 3 can also be an end node, okay? Now, if I'm doing node coverage, okay, the test requirement says I need to go to 1, 2, and 3. 5. Let us think of a number of test cases that would cover that, okay? I'll think of test case 1, which is 1, 2, and I'm out. And then test case 2, 1, 3, and I'm out, okay? Now, when I look at 1, 2, and 1, 3, looking at 1, 2, and 1, 3, that means I have actually satisfied the 3 tests. So here's 1 covers 1, 2 covers 2, and the 3 over here covers 3, which means I've satisfied test requirement number 2. Sorry, I've satisfied the entire set of test requirements, which means I've satisfied node coverage. 5. Can somebody tell me, for edge coverage, what are the test requirements? Now I'm looking at the edges this time, huh? These are my edges. Can somebody tell me? All right, so I got 1, 2. Just a moment. 1, 2.
2, 3.
2, 3.
1, 3.
And 1, 3. 5. Before we move on, let me take those test cases that I've created for the weaker coverage criteria, okay, and see if it satisfies the test requirements for edge coverage. Okay, so we got 1, 2. Well, we got it over here, so that this one is good. We got 1, 3, so that one is good, but we don't have 2, 3. Okay, well, you never know. It might have been we had a bug that was between the edge of 2, 3. And so had we just satisfied coverage criterion node coverage, we might have not have caught that bug, okay? All right, so for me, I would have to use all of these test cases, okay? 1, 2, and 1, 3, and I probably would have added 1, 2, 3, just to make sure that the 2, 3 part is satisfied. So I'll take a look at this 2, 3, and I say, now I've satisfied, okay? Matter of fact, I don't even need the first one. I wouldn't have even needed the first one. So 1, 2, 3, 1, 2, 3, and 1, 3 would have been fine. I would have covered all the different edges that I had. Now, one thing I was saying, which is funny, it says this thing about length up to 1. Now, what this is trying to say is, okay, I'm just gonna decipher the that code over here. Sometimes we have a situation where we have a graph that looks like this. The graph is nothing but a node. And so you'll say node coverage, okay, the test requirement is 1, but I don't see any edges. So with that means the test requirements is nothing. And you said, doctor, that anytime I'm going to go for a higher coverage criterion, it always subsumes the lower one. Well, it's not subsuming in this way. And this is where the length up to 1 part is there, so that it forces us in a situation where I have a graph that doesn't actually have a node to contain that one particular situation of a graph that contains a node and a node only, or just a graph where a sub graph. So I have the situation over here. So I got one, and one could have been an end node. Yes, it could have been a different subgraph over here, but still this part of the graph is basically one node. Okay, and they write down the length up to one part so that you have to include node one, although it doesn't have any edges along with it, but it becomes part of the test requirements for the edge coverage. Okay. So we just talked about this here. That was actually the example that I was just mentioning a moment ago. Okay. From this point on, the higher levels of coverage criterion is basically based on increasing the number of edges that we need to cover. Okay, so when we said edge coverage, we were talking just edges of one. Okay, next up is edge pair coverage. Okay, so edge pair coverage is coverage of length of two. All right, and you'll see that length of two would require more test cases than edge of one. Let's see an example of this. Okay, so if I have a situation as such, edge pair, let me see. Okay, this is a definition. Okay, I have a situation as such. One going to two. If I remember this correctly, I should have tried to remember that better. But anyway, okay. Edge coverage, okay, would be what? 1, 2, صح? And what else?
2, 1.
And 2, 1. Edge pair coverage would be, no, 1, 2, 1. Okay. And then the next one would be 2, 1, 2. Now, edge coverage, one edge, you always look at how many commas. Just a single comma. Edge pair, you look at how many commas? 2. Okay. Next up, 3 edge, 3 commas. 4 edge, 4 commas, and so on. Type. Okay. To take edge coverage, I could have had a test case that goes 1, 2, back up to 1. Okay. Back up to 1. Okay. Let's just assume there's an exit over here, just to make it fun. Okay. So that would have covered edge coverage. Okay. By just the one test case. This one test case is not enough for edge pair. Okay. For edge pair, I would have to go in 1, 2, 1. But then again, I had to go 2 at least before I take out that exit. So that's a more thorough test case edge coverage. All right. And so on and so on and so forth. So let's just say I have 3 edge coverage. I would have needed 1, 2, 1, 2, and then 2, 1, 2, 1. Okay. In order to satisfy the bottom one over here, I would have required 1 loop. Okay, like a 1, 2, followed by 1 and a 2, followed by another 1 and a 2. So for 3 edge, I would have actually required to go through the loop basically 3 times, whereas edge pair twice, whereas edge maybe just the one time. Okay, and as you can see, as we go higher in the number of edges, the more thorough and the stronger the coverage criteria is. Okay. Is this clear for everyone before I move on? Guys at home? Clear? Yep. Right. Abdul Nasser, is it clear? Everything is clear?
Yes.
Okay. Type. So you keep saying, maybe you're thinking, okay, Dr. Attar, we're just increasing the number of edges. Why don't we just look at the entire path? Okay. We call it complete path coverage. Okay. يعني let's just نجيب من الآخر زي ما نقول يعني. Okay. Now, complete path coverage obviously is good. It's the strongest because for a certain graph size, I've actually created a coverage criteria that is as big as it can get. So if I have a situation as such, 1, going to 2, going to 3, going to 4, going to 5, okay, well, I got 1, 2, 3, 4 edges, okay, so I'm going to go 4 edge coverage, okay, 4 edge coverage, all right, instead of going 1 coverage, well, edge pair, well, 3T, well, so on, okay, so I'm just going to the maximum size. But the problem is, we get to face the problem once we have a situation as such, okay, where we have a loop. Because once we have a loop, the number of edges, the number, of paths become infinite, okay? Because if you go back over here, 1, 2 is a path, 1, 2, 1 is the path, 1, 2, 1, 2 is the path, 1, 2, 1, 2, 1 is the path, 1, 2, 1, 2, 1, 2 is the path, and so on and so forth. We can just keep looping forever and forever, okay? So complete path coverage, had we just had a straight line or a tree-like structure in our code, yes, it would have been feasible. But once we hit a loop, then it becomes infeasible. One way we can handle this is we use something called the specified path coverage. And specified path coverage is basically a situation where I'm sitting down with my customer, my analyst, my design experts, and I look at it and I say, okay, let's just cover those particular paths because these are the ones that I'm expecting to be executed 90% of the time by the users of the software. So these are the ones I want to focus on. And obviously at this point, it hasn't become a structured approach to structural coverage. It's rather just what do we feel should have priority um, uh, in terms of the different paths in my graph, okay? So if I look at this graph over here, node coverage is the requirements 0, 1, 2, 3, 4, 5, 6. Okay, I could have done that by 2 different paths. So let me just say 2 different test cases, should I say. So the first test case takes us, let me go actually take highlighter actually better. So the first one goes 0, 1, 2, 3, 6. Okay, 0, 1, 2, 3, 6. That means we still got 4 and 5 are left. The second one takes us 0, 1, 2, 4, 5. Guys at home, how many test requirements do we have for edge coverage? Requirements do we have? Test requirements for edge
9.
coverage.
9.
9. Sadun. Who else is there? Let me see the participants. There's a lot of people. Girls. I didn't actually. Yeah, Banan, Faye. All right, guys, I need you to speak up. Sorry, how many? Edge coverage. All right, so we have 8. مين يزود? Girls, I haven't heard anything from you just yet. How many test requirements do we have for edge coverage? Okay, Banan says 9. Okay, so let's take a look. We got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and basically you're just counting the number of edges. Okay, so you got 1, 2, 3, 4, 5, 6, 7, 8, 9. Oops. Yeah, each one counts as an edge. Okay. Even self-looping is considered an edge. No, two different edges. Yeah. Okay. So edge pair coverage. Now we're talking about pairs. Okay. Now, when you're doing this, don't just do it the hot dog way. Okay. What I want you to do is take the number 0 and see how many you can create with two edges. Okay. And once you've exhausted, you move to number 1 and see how many you can create with two edges. Okay. Yalla, go ahead. Until you've reached the last one. Yes, it's gonna get tricky. Yes. No. You begin with 0, and you take the numbers, you go up ascendingly on the numbers, 0, 1, 2, 3, and so on. Then begin with the 0, and you see how far can you get with two edges. Okay, so I'm gonna do this for you. So the first one, yes. Okay, so I got 0, مثلا هنا 0, 1, 2, that's 1. And then 0, 2, 3, and 0, 2, 4. So from the zeros, this is how far I've reached. Next up, I take the next number. I take 1. No, I take them all of them. Okay. Okay. So guys, how many test cases? How many
13.
other test requirements?
13.
13. Okay, girls. Well, if there's an arrow that's going you back, then fine. But as you can see, that the case doesn't exist. 13? I don't know. Okay. On a piece of paper, guys, huh? Right. Now, if you are looking at the screen and just doing it with your finger, you're gonna get lost. So we have Faye here with a 10. And then what's your answer? Okay. So since you guys are lost, okay, we'll do it this way. Okay. Okay. Let's just do it in a structured way. We said 0, 1, 2. That's 1. Type. I got from also we can go 0, 2, 3. And then we got 0, 2, 4. صح? All right. This is how far we've got with the zeros. Next up, 1. Got 1, 2, 3. And then I got 1, 2, 4. And that's it. This is how far I can reach with the number 1. Next up, 2. Okay. I got 2, 3, 6. And then I got 2, 4, 5. I got 2, 4, 6. صح? Right? Next up, number 3. I can't have anything with two edges with number 3. Number 4. Okay, I got 4, 5, 4. All right, I got 4, 5, 4.
5, 4, 6, and 5, 4, 5.
And then 4, you said 5, 6? No, there's no such thing as 4, 5, 6.
5, 4, 6,
Yeah, 5, 4, 6.
and 5, 4, 5.
Okay, so we've exhausted the 4s, صح? So now we move on to 5. We got 5, 4, 6. We got 5, 4, 5. And always, Abdurrahman, we will go with the smaller numbers first so that we don't get lost. Okay. Next up, we look at 6. Wallah, there's nothing we can do with the number 6. So now let's begin counting. Got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Let's just remove. Okay. Got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right. And then as we look at the test requirements, in order to satisfy them, okay, how do we know we're going on the right path? By the way, before I actually get into the satisfaction thing, if we look at edge pair coverage, we were actually doing the same exercise that I was just doing with edge pair, but we're looking at 1 comma. So I looked at 0 and I said, how far can I get with 1 edge? Okay, 0 at 2, right? And then that's as far as I can get with 1 edge. Okay, if I'm really, really lost, then I get 1, okay, and I got 1, 2. So this systematic way can be applied. Oops, no, it's not 1, 3. Can be applied on any length. Okay, 2, 2, 3, and then I got the 2, 4. Okay, and then I pick up the next one, 3. I got 3, 6, and that's it. And then I pick up the next one, 4. I got 4, 5, and I got 4, 6. The next one, 5. I can get to 4, and that's it. This is how far I can reach, and obviously 6 can't take me anywhere. And this is how I've done it. So the way we were actually doing it with edge pair coverage is the same exact way we were actually doing it in edge coverage, except for in edge coverage, the way we were tackling it in an ad hoc way. So we'll learn from this point on to make sure that we don't just eyeball it anymore. We have to put down the numbers. We write them down on a piece of paper. And I suggest you actually pull down a piece of paper now, because it's gonna start getting a little bit complicated from that point on. Now, a moment ago, when we looked at node coverage, I looked at I did it with the highlighter. Okay, but really, there's actually a more structured way to do it. Okay, now the more structured way, here I am. I'm still back at node coverage. Okay, I look at my test coverage and I see what's inside my test path would cover my test coverage. So I got the 0. It looks at it. I say I got the 0. I got the 1. Here's the 1. 2. Well, I got the 2. 3. I got the 3, and then I got a 6, and I got the 6 over here. Meaning that my first test case have left 4, 6 open, which means I needed another test case. And then in my next test case, I see the 4, and then in the 5, and now I can tell that this covers that one. Okay, 5. You'll notice let's just actually go with edge pair coverage. Okay. With edge coverage, it's the same exact idea. So 0, 1, I got that over here. 0, 2, I got that over here. 1, 2, I got that over here. 2, 3, got that over there. 2, 4, got that over here. 3, 6. All right. So I can, in the exam, if you're doing this in an exam and you want to make sure you haven't lost something, okay, this is how you do it. 4, 6, 5, 4 is where is right here. So I can say that these two have covered my test requirements for edge coverage. Okay. Finally, so edge pair coverage, we said we've got, I can't remember, we say we got 10, 11. Okay. Okay. So we have 11. Let's, before we think of the test cases that we need to cover those 11, let's take the same test cases and see if they cover my test requirements for edge pair coverage. Okay, so I'm using these test cases. Maybe, or maybe not, they won't cover it. We'll see. And I'm gonna see if they cover the test requirements for edge pair. Okay, right. 0, 1, 2. Do we have it, guys?
Yes.
From the, so we got it. Yes. 0, 2, 3.
No.
Huh? We don't got it.
No.
Okay, there's nothing here from the above that has a 0, 2, 3. So we already know right away. No, it's gotta, because these commas represent a flow. Okay, like 0, 2, 3. This is what it means. Okay, it's not just filling in the gaps. Okay, type 0, 2, 4. Do we have it?
Yes.
Okay. 1, 2, 3. Yes, it's right there. 1, 2, 4. No. Oops. No. 2, 3, 4. 2, 3, 6. Yes, it's right there. 2, 4, 5. It's right there. 2, 4, 6. No. 4, 5, 4. Yes, right there. 5, 4, 5. No. Okay. And then finally 5, 4, 6. Yes, we got it. Okay. So right away I can see I got 3 different test requirements that weren't covered. And so I would have needed something to take me through them. So one thing I noticed myself I'm missing is I'm actually missing going like this. That's 0, 2, 3. Another thing that I'm missing is I'm missing going like that, 1, 2, 4. Another thing that I'm missing, 5, 4, 5. So going like this. All right. So at least this one, I have to come up with a test case. Maybe it goes like this. So that takes care of this one over there. Okay. And then the next one, I can just go 0, going down this line. Actually use a different, no, I wanted to use a different color. Okay. I'm going down this road to the 5 and then go back up. Stop working. Unfortunately, I think it just froze on me. Yeah. It does that sometimes with the highlighter. But I think you get the idea. So I go down to 5, then go back up to 4, and then I have to go down. Oh, froze completely. Oh, okay. So a PowerPoint just broke on me here for a second. So I gotta just open it up again. Just give me a moment. Are you guys still on here?
Yes.
Yes. So PowerPoint just froze on me. So I just gotta can't remember what slide number we were. No, we haven't reached here yet. We haven't reached here. Yeah, there we go. We're in this one. Okay. So, oh, come on. Anyway, in order to get to, what was it? 5, 4, 5, 4, 5. Yeah, I think it's just okay. Yeah. Next time I have to bring